All right, hey eighth graders. Um, today we had a quiz in class. I messaged a few of you. Still waiting on some responses. It does need to be taken. Something you'll want to study before you take that is your notebook and diagrams and stuff like that. Your Marianas Trench and Island worksheet. This is due today at midnight, and then this was just for the kids after they got done doing the quiz. Okay. Just a little review. So we kind of went over coordinates last week. Here's like a practice coordinate. So 45 degrees north by 112 and a half degrees west. And so previously I almost put 112 and a half degrees east. That's wrong, right? It's west. Okay, so I find, 112 and a half degrees west. Here it is. So I follow this line of longitude up here till I hit my 45 degrees north, and boom, I found them, and this is where it looks like this would be somewhere in northern Illinois or maybe Iowa. Okay, so let's just remember kind of jogging the brain of how to do coordinates, because today we're actually going to do mapping volcanoes and major earthquakes around the world. Um, and so let's take a look at this. So we're talking about volcanoes at first here. So let me back up here. All right. So this is what we drew on the board today. So we've already kind of drawn this guy here, right? We have seafloor spreading going on here. We have a mid-ocean ridge. We see this oceanic crust is spreading. It's going away from the the mid-ocean ridge, but it's subducting here, right? And this subduction, it causes uplift. It causes mountains. And so uplift, if you think about the United States or the North American plate, and then we have a oceanic crust that's subducting, right? As it's subducting, it's not just pushing the tip of it up, but it'll push the tip of it up, but then also the entire angle. So as you're going from like Illinois to Missouri, it's relatively flat. We sit at about 500 feet above sea level where we're at right now, or 300 feet. I can't remember exactly. We're a couple hundred feet above sea level. Anyways, in Missouri, it's about the same. As you start going across Nebraska, you start going up at a slight angle. And by the time you get to like Denver, Colorado, you're already at about 5,000 feet above sea level. So then once you hit those mountains, because literally you get to Denver or something like that, then you see boom. And then you see these mountains that just jut up out of the ground out of nowhere. But anyways, we talked about two different types of volcanoes today. There's shield volcanoes. There's a couple other volcanoes that are kind of escaping me right now. But today we just went to dormant volcanoes and active volcanoes. And so how do we know if something's dormant? How do we know if it's active? Well, we know if it's active if it's erupting, right? Well, volcanoes, since it's geologic time, right? Geologic time is a long time. Like, it's hard for us human beings. Most of us only live to be about 75 or 80 years old, right? Where volcanoes are millions of years old. So if it's active volcanoes, they consider those active if they're erupting, have events at least once every 1,000 years. If they don't have an event after 1,000 years, or they're done having events, then we call them dormant. And so how do we know if something's like truly dormant if we don't think it's going to erupt ever again? Well, let's take a look at this. So we know as this oceanic crust right here, it begins to return, right, as it's subducting beneath the continental crust here. As it's subducting, it's going back into the earth, right? So we know that back into the mantle, it's going to recycle. It's going to get melted. Well, anyways, this crust here actually has a low melting point. So it melts fairly easily at a low temperature, relatively low temperature. I'm not saying it's cool or anything. But anyways, as it begins to melt, it will rise up and cause these magma plumes, and these guys will begin to melt and eat through this rock into the mountain range, and then we have some volcanic mountains in here, and we have some volcanoes in there. So this would be considered an active volcano range here. That's not really a scientific term, but this would be considered an active volcano because as long as, I got it right here, as long as the boundary has a subducting plate, there will be an active volcano above it. Why is that? Because we're feeding it fuel, essentially, to melt and to keep rising. So this volcano will keep on erupting as long as we're giving it this oceanic crust that will continue to melt and will continue to rise through this little volcanic vein. So there's one way that we know that this guy's going to be an active volcano. Now, if we look at something like hotspots, This is just like a big old crust plate slab. And then we have a hot spot, which is essentially just a big magma chamber. All a magma chamber is just a big chamber full of magma, right? And it's going to get hot and it's going to melt away at the crust here. And so let's take a look at an example that I got here. Okay, so if I zoom out, so there's our axial volcano. You guys remember looking at this guy? Here's our Juan de Fuca plate. Here's Oregon, California. Oh my gosh. Anyway, this is Google Earth. You guys should be familiar with this guy. I love Google Earth. It's the coolest thing on the face of the earth. But here, this is what we're looking at. So this is actually the Hawaiian Islands. Okay, and these guys were all created by volcanoes. They all have volcanoes on them. Let's see if we can zoom in and take a look at some of these guys. Here's Moana Key. I have no clue if I said that right. This looks like a volcano right here. Moana Lau, maybe. So all of these guys, you can see how volcanoes have formed these. Here's some other volcanoes. Here's another volcano. Here's a volcano. So on and so forth. Kilauea. Ooh, Kilauea. This was the one that was erupting about 2 years ago. It was erupting for about 9 months straight, and they had to move a whole bunch of people away from this area because obviously you can't stop a volcano from erupting. Okay, but we keep chasing this. And we see some smaller volcanoes. We see some of these guys. Oh, and they start getting smaller, and they start disappearing underneath of the ocean. We start to lose them, and so we can follow this chain all the way up here. So what the heck's going on here? Well, there's no break. This is no plate boundary. Okay, this is actually all right here. This is all the Pacific Ocean. So what's going on right here? Well, there's actually a hot spot right here underneath the Hawaiian Islands. What's going on is this Pacific plate is moving, right? The crust is moving over top on the mantle, right? It's moving over top the mantle. And then we have this magma chamber down here, and it's poking holes through the crust, and it's creating these volcanoes that make these islands. Well, it keeps erupting. Well, my crust keeps moving. So this guy's stationary, my magma chamber stationary, but my crust moves over top. So he'll poke holes into the crust, make an island there. But then as he begins to move, then my magma chamber then starts to make another hole right here. And then as my crust moves, it will make another hole. And because magma wants to go straight up, right? It doesn't want to have to move laterally and then up. So it'll move a little bit with the crust, but then eventually it gets too hard to keep up with that current, that lava current that's keeping that volcano alive. And then that lava wants to go straight up because that's the weakest point, or that's the path of least resistance, and it'll poke a hole through the crust again. And so that's what's been happening. So we can trace it all the way up to here. This is where some dormant, these are all essentially dormant volcanoes that we see here. Magma was coming out of these guys, and these guys potentially could have become islands, just like the Hawaiian Islands. And some of them are probably still there. The island, here's Midway. This guy, there's probably, here's the air landing strip. This guy was essential back in World War II. If you guys remember, there's the Battle of Midway. But anyways, what's also really neat about this is when we think about plate tectonics, we think that they move in lines and they never stop, right? They just move in one straight line and they don't move up, down, left, right. This shows that at the beginning, our plate was actually moving up, okay? And so our magma chamber our hotspot has always been here, right? It's just been the plate that's moving over top of it. Okay, so this spot, at one time, this spot up here was actually right here because our hotspot stays in one spot. And so what happened is our plate moved up and to the left, or to the east, right? He's still moving to the east. And so what's going to happen, or what can we predict to happen? Well, these islands here, these are the active volcanoes here. I'm not sure if these volcanoes are active over here, but I'm pretty sure these ones are all over here. Well, anyways, and you got to think the magma chamber underneath of these are absolutely massive. They're huge. Anyways, so what can we start expecting? Well, it looks like we got something going on here. Is it possible? Whoa. Is it possible that we have some young volcanoes starting to form here from this magma chamber because these guys are being pushed over? That's actually probably what's going on here. These guys, these are other little underwater volcanoes that we see sprouting up, and so it just depends. Could any of these guys could be a candidate for the next island that's going to form here? And so these guys are going to move. This plate's going to move this way, but you got to think, like I keep saying, the plate moves, the hot spot stays in place. Okay. So anyways, and that's all this kind of was talking about is our crust moves, our hotspot stays in place. This hotspot is stationary. The tectonic plates move over top the hotspot, producing more volcanoes. And when you produce more volcanoes in the ocean, and if they stay there long enough, or they spit out enough lava, eventually they'll rise hundreds of feet or thousands of feet and finally break through the sea surface and then create the island that it's on, right? Okay. So, and finally, the last little thing on that. We went over our 3 different types of plate boundaries. So we have 3 types of plate boundaries. We have a divergent plate boundary. This is where plates move apart, okay? And so where can we see an example like that? So this is like seafloor spreading, right? We have crust being created here, and as new crust is being created, older crust is moving away, older crust is moving away. What's a good example of that here? Our mid-Atlantic ridge. So this guy right here, new crust is being made here. Older crust is out here. Older crust is out here. So the crust right here that's right next to Africa, or the crust that's right here next to Brazil and French Guyana, these guys were made at about the same time, and so on and so forth. So this is our youngest, older, oldest. Okay. So this is a divergent plate boundary. Our next one on our list here. Keep on clicking the wrong thing. Convergent. This is where they come together. So where can we see a convergent plate boundary? Well, anywhere you see mountains. So right here, here's a convergent plate boundary. We can see this dark blue line here. This is a trench forming. Another example. So that's obviously obviously continental crust, and this is oceanic crust. Over here we can see it. This is another trench. That we haven't talked about yet. I'm not sure if this really has a name. Doesn't say that it's got a name. Oh, there's something here. Tonga. Okay, those are some islands. But there's oceanic crust and oceanic crust that's doing that has a convergent plate boundary. Here's our Marianas Trench, and we have again oceanic crust and oceanic crust where the Pacific plate is subducting beneath the Philippine plate. So that can also happen. So here's a convergent plate boundary. And then finally, we have a transform boundary. This is where these guys slip past each other. So I have plate A going one direction, and I have plate B going the opposite direction. And they'll slide, and then they'll catch on each other because they're not perfectly flat, right? They catch on things. They're rough and rigid, right? So they'll catch on each other. Well, they don't stop necessarily. They keep on building up pressure until finally they build up so much pressure that rock breaks, so they're able to slip past each other, and then that's how we get things like earthquakes and such. Okay, so now that we got through that, so here's where your assignment is. So here, you guys, I gave this out to you guys last week, you remote learners. We didn't get to this last week. Today's the first day that we actually got to it. So if you finished it or you started doing it, just know that I'm only having you do procedures 2 and 3 today. So procedure 1, it says draw arrows, include the directions that the plates are moving. So if we see this, that's already happening. If we see this other one, it's already happening. You don't have to do anything on this page, okay? Do not draw anything on this page. You don't need to draw anything on this page. This is a nice page to look at boundaries. So here's our mid-Atlantic ridge here. We see that the plates are moving apart. Here we see a convergent plate boundary. So we see our mountains are being made under here, right? Mountains are being made here, so on and so forth. But the one that we're going to actually do work on is this guy right here, because this is our coordinates. Because what we're going to do is you guys are going to map the major earthquakes, and you guys are going to map the major volcanoes. Okay, so if I want to do volcano A, you guys are going to have to print this out. So if you can't, please let me know, and we'll see if we can figure something out. Maybe I can find like something else online. But if you cannot do this, please let me know. So I have this volcano A. I'm going to call it volcano A because I don't know how to pronounce that. So, anyways, our latitude is 35 degrees south and our longitude is 70 degrees west. Okay, well, let's go over here. And so I wish I could tilt this on smart on my smart notebook. But anyways, what I'm going to do is it was 35 degrees south, not north, right? Pay attention to whether it's north or south. So it's 35 degrees south. That's roughly, right? It doesn't have a 35 degrees south, so I know that 35 is exactly between, or it's between 20 and 40. Not exactly half. It's a little over halfway. So here, I'll mark that right there. And then it said 70 degrees west. Well, I know it goes 40, 60, 80. Well, I know that 70 is halfway between 60 and 80. So it's about right here. So I'll go halfway. And I know, like I said, here's my 35 degrees south right here. So I'll chase this until these two guys run into each other. Well, look at that. That looks like, let me get a different color here. That looks like it's right in our Andes mountain range. That makes perfect sense. So our first volcano, these are real volcanoes and real earthquakes, by the way. So these aren't just made up. So we have a volcano that's right here in the Andes Mountains. Okay, so your guys' job is to do, so I said do procedures 2 and 3. Procedures 2 and 3 is just talking about locate volcanoes, and 3 says locate major earthquakes. So for the volcano, do one color. So I'm doing it in red, let's say. And then for earthquakes, I'm doing it in blue, let's say. Okay, make sure that I know which ones you're doing. So that's all that's due for Monday is just map those two, map this table on here. And you guys are good to go. So just this map right here. You don't need to do the questions or nothing else. Okay? All right, other than that, if you guys have any questions, let me know. And please keep in touch. Bye.